All right, let's talk about LR circuits. As the name suggests, now we have an inductor with a resistor. And if you're wondering, okay, how do you get current going through it in the first place? You first have it hooked up to a battery. So instead of your normal switch, this is a switch where it doesn't break contact with the wires at any point. So at no point does it completely um, uh, have an open circuit. So you can see kind of the round part. It's like a sliding switch. Okay, so at the top we have a resistor. On the side we have our inductor. And so there's kind of two circuits going on here. While it's switched up, the current is going clockwise, and it goes from the battery through the resistor and through the inductor and back. So that middle bar is basically doing nothing. So we'll say, it starts at pointing at A. So what happens when you switch it to B? When you switch it to B, you essentially take the battery out of the picture. And so the current that was already going through the resistor and the inductor, there's nothing to drive it anymore. And so you would think that the current would just disappear. But the inductor stops that. That would be almost an instantaneous change in current. And so what the inductor will do is it'll resist that change. And by resisting that change, it will actually create a potential not against the current, but in the direction of the current. Because again, the current is decreasing, it will oppose it, so it'll actually create a potential in the direction um, of the current. Um, Now, since the current's already going clockwise, we'll try and keep with our traditional convention, where since the current is going through the inductor, we'll consider the inductor as if it were a negative or a potential drop. But you'll see that hidden inside that DIDT, since DIDT is negative in this case, that's how it's actually going to offset. But we'll just keep to convention, um, and it will actually work itself out. So you notice in this case, instead of being a second order differential equation, it's actually a first order one. You have current in the resistor term, and then you have the derivative of current in the second term. And so again, once my left hand gets out of the way, um, you'll if you rearrange it, it essentially turns into exponential decay. Um, so just rearranging, you bring um, collect your current terms on the right, your constants on the left. I'm just writing it as the 1 over L over R, so that later on it'll become one, almost one constant. It'll be easier to work with. Okay, so you collect your current terms. When you integrate, now you're integrating from the initial current to whatever current at some time later. That new current will actually be less, but it really doesn't matter. That's where the exponential decay is going to come in. Um, and so this is exponential decay pretty much just like an RC circuit. In an RC circuit, you had a capacitor that would attach to a resistor, and the resistor would slow down the rate at which the capacitor could discharge. In the same way, what you have here is you have current going through the inductor, and the inductor, again, slows down the rate at which the current can dissipate. Um, and so you get that uh, exponential decay, and now your time constant is L over R instead of um, or whatever it might be before. Okay, so you have this inductor, and there's current going through it. So let's take a look at a couple of different other things that go along with it. For example, the potential. I believe that's what I'm getting at here. Oh yeah, okay. So the potential across your inductor is we've had that before, or we defined that before. That's L d I dt. Again, my hand is just all up in the way. But as soon as it gets out of the way, you will see your potential across your inductor. That's your negative L d I dt. And when you actually take the derivative of their current function, which we have now, um, and substitute it in, I don't remember why I was putting it. Oh yeah, you'll see that the resistor initially has all the potential across it, um, but once you switch over to the once you switch the battery off, your inductor is what's providing your potential now. So that way you don't violate Kirchhoff's loop rule. So Kirchhoff's loop rule still works. You can see that essentially what happens is you have exponential decay of the potential across your inductor as well. And that potential starts off at the potential of the battery the moment the switch changes so that the battery gets disconnected, and then what drives the current is now your inductor. So your inductor starts with the same potential as your battery so that it drives the current through your resistor. Your resistor then takes away that potential, so your inductor is essentially your EMF, and then that EMF exponentially decays when you switch. So very similar to an RC circuit. You have exponential decay.